As it says at the top of our notes, what we're going to be doing here in the final lesson is graphing sinusoidal functions. What a sinusoid is just any function that is a cyclical curve. So it's something that is going to be repeating over and over and over, like a sine function or a cosine function. It's a function that has cycles to it. So consider the sine function that we've worked a lot with. That's sine of theta. What is its value when? And we'll just take a look at a few of these. These should be some special angles that we're really familiar with. So when theta equals 0, that says sine of 0. And we know that on the unit circle, if we were just to sketch that out really quickly, at 0 radians, that's the point 1, 0, our y-coordinate is 0. So sine of 0 would be 0. If theta were pi over 6, we can look back to the unit circle. That is our first special angle. At that point, the y-coordinate is 1/2. Hopefully we remember that. And then we have sine of pi over 4, which is 1/4 of the way to pi. And that's going to be halfway in the middle of quadrant 1. So that is our y-coordinate of radical 2 over 2. Then we've got sine of pi over 3, which would have a y-coordinate of radical 3 over 2. And then finally, sine of pi over 2. And that's this point right here. That's the point 0, 1, so sine of pi over 2 would be 1. So what we end up with is all of these values that are the output when our input is theta. And we know that anytime we've got an input and an output, we can use a function to represent that situation and just keep replacing that input and see what the outputs continue to be. So it's going to be useful to track this function as theta changes, and we say over this interval from 0 to 2 pi, because remember, as we travel around the unit circle, we have 0, then we have pi over 2, then we have pi, then we have 3 pi over 2, then we have 2 pi. We could keep going if we want to, but from 0 to pi over 2 would be that interval there. So what's going to happen if we graph sine of theta for one full rotation of the unit circle? That's essentially the idea here. So we're going to use this space to graph what all of those outputs are over that interval. All right, so we're going to go from 0 to 2 pi. And in the middle of that, we're going to have pi. That's obviously halfway between 0 and 2 pi. And then in the middle there, we're going to have half of pi. And over here, this is our halfway between pi and 2 pi. So that's 3/2 pi. Now we've also got 3 more points which we're going to plot because we took the interval from 0 to pi over 2 and we split that up. We actually have 3 angles even just in that range there. So we're going to have our pi over 4. We're going to have an output there because we know what sine of theta is when theta is pi over 4. And we've also got a pi over 3 and a pi over 6. I'm going to be careful not to have those be the exact middle because they're not halfway between pi over 4 and pi over 2. All right, so let's plot the points that we've got so far, and this is just like plotting any function, right? So sine of 0 is 0. So I've got a point at 0, 0. That's 0 on my x-axis, and let me give my y-axis a label here. I'm going to say this is probably going to oscillate between 0 and 1. We'll see why that is in a moment. Then we have pi over 6. At pi over 6, my output is 1/2, so halfway to 1. And then we've got radical 2 over 2, radical 3 over 2, and 1 for our outputs at pi over 4, pi over 3, and pi over 2. And I'm sort of approximating where that radical 2 over 2 and radical 3 over 2 are going to be. If you want to put those into a calculator, you'll see exactly where that is. And we also know that the function exists everywhere in quadrant 1. It's not like it only exists at these points. I could have plugged in pi over 7, 2 pi over 18, right? There are a lot of things that I could have plugged in here that I just chose not to. So we're going to connect these points because we know the function exists between those points. So this is what the function looks like when I graph it between 0 and pi over 2. And then in part 3, we're asked to continue the graph of sine of theta by evaluating the function for the special angles in quadrant 2. So let's take a look at the angles in quadrant 2. So I've gone ahead and written down the special angles in quadrant 2. We've got 2 pi over 3, we've got 3 pi over 4, we've got 5 pi over 6, and then of course we've got pi there. So sine of 2 pi over 3, it's going to have the exact same output that sine of pi over 3 has. So that's just going to be radical 3 over 2. Sine of 3 pi over 4 is going to have the same output that sine of pi over 4 has using that reference angle there. That's going to be radical 2 over 2. Same process here for 5 pi over 6. That's going to have the same value as sine of pi over 6, so 1/2. And of course pi is a point that we know very well. That's negative 1, 0. Sine of pi is going to be 0. So we can add those points now to our graph. I can leave them on the page here. I'm going to want to add in these angles. So halfway in the middle here is going to be 3 pi over 4. And then we're going to have our 2 pi over 3. And our 5 pi over 6. So this is the point radical 3 over 2, here's radical 2 over 2, here's 1/2, and then 0. And so as I continue this function, it comes right back down to 0, which should be no surprise because we know that sine is tracking our y-coordinate, and as our y-coordinate comes up, it reaches a maximum of 1, and then that y-coordinate reaches a minimum of 0 over this interval. So you might be noticing what's about to happen with the rest of this sine function as we continue it through our interval from 0 to 2 pi. So we're going to do the same thing for quadrant 3. I'll go ahead and list in our special angles here under number 4. So these 4 would be our special angles in quadrant 4, and I guess 3 pi over 2 is not in quadrant 4, but we're just going to continue the pattern here. Go ahead and evaluate sine of each of these angles. All right, so sine of 7 pi over 6 is going to be the same as sine of pi over 6 if you negate it because we are into quadrant 3. So now all our y-coordinates are negative. So that's going to be negative 1/2. Sine of 5 pi over 4, that's the same as negative sine of pi over 4. So negative radical 2 over 2. Sine of 4 pi over 3 is going to be negative sine of pi over 3. So negative radical 3 over 2. And then sine of 3 pi over 2 is going to be negative 1 because that's a point that we're very familiar with on the unit circle. So we'll go ahead and add those to our graph. Okay, so 7 pi over 6, that's negative 1/2. And then we are approximating the next few. Radical 2 over 2, radical 3 over 2, and then, of course, negative 1. So I can continue the curve all the way down to 3/2. All right. And you can probably guess where this is going next because we've graphed this thing through quadrant 3, so we still have to graph through quadrant 4. We're definitely going to end up right where we started because we will have completed a full circle. So I know that 2 pi is going to be 0, just like how sine of 0 was 0. But let's go ahead and write in those values next to question 5, just so that we've got them there. So sine of 5 pi over 3 is negative sine of pi over 3 using the reference angle. So that's going to have a value of negative radical 3 over 2. Negative sine of pi over 4 is going to be negative radical 2 over 2. And then negative sine of pi over 6, negative 1/2. And then 2 pi, just as we said, that's going to have an output of 0. So we can go ahead and add the rest of those into our graph. All right. So what this is a complete graph of sine of theta And we could say y equals, we could use x here, and we will for some of these, over the interval from 0 to 2 pi. A couple of things that it's really important to point out with any function are what are the domain and range of this function. Well, you might be tempted to say that the domain of sine of theta is from 0 to 2 pi, but we restricted that domain. We said only graph it there because we know that the unit circle is not bound by just 0 to 2 pi radians. We could keep traveling, right? 2 pi, we could keep going around to 4 pi, we could go around to 6 pi, and then around to 8 pi. There's no limit to how far we can go. And the same is true in the negative direction. I could start and I could travel negative 2 pi, then I could go to negative 4 pi, and I could do the same thing in that direction too. So the domain of sine of theta is all real numbers. We've restricted it here just because we're not going to graph it forever, but that would be the domain. And the range, you'll notice, it's always going to oscillate between 1 and negative 1 when the function is just sine of theta. And that's because if you look at that unit circle, you're going to see that the function never breaks any higher than 1 or negative 1. And I'm saying higher because we're talking about sine. But since sine is your y-coordinate, we're noticing that it's 0 as the y-coordinate, and then the highest that y-coordinate ever gets is 1, and then it comes back down and it passes 0, and the lowest it ever gets is negative 1. And it's just going to keep bouncing between 0 and negative, or between 1 and negative 1 rather, never growing higher or lower than that for the y-coordinates of those points. So the domain and range, something to keep in mind. And then one more question for us to consider here. Before we wrap this lesson up, consider the fact that we have just completed one full rotation of the unit circle. What would happen if you sketched sine of theta over 0 to 4 pi instead? And then what about over negative 2 pi to 2 pi? So I'm just going to put a couple axes down for us to sketch this out on. So we saw that when you graph this function from 0 to 2 pi, sine reaches a maximum here at pi over 2, then it hits 0 at pi, and then it hits negative 1 at 3 pi over 2, and then comes back to 2 pi. So this is what the function looks like between 0 and 2 pi, and it's just going to keep doing that if you do another rotation around the unit circle. So it's just going to continue on. And if you want to keep going to 6 pi, it's just going to keep doing that as well. The same is true if we go in the negative direction. So again, if we take a look at the graph I've got down here, here's 1, here's negative 1. If we were to graph what we graphed earlier, and there's pi over 2, here's 3 pi over 2, well, you'd have a function that looks like this. Not perfect, but there we go. Should go to 2 pi. All right. And it just keeps going like that in the negative direction. So I could continue with my negative pi over 2 being here and my negative 3 pi over 2 being here. It's just going to keep going, oscillating back and forth between 0 and negative 1. And we'll talk about the cosine function in our next lesson.